So welcome to my presentation towards optimal defenses on adversarial examples for deep neural network-driven digital twinning. We'll be covering three key concepts: metaverse, the digital twinning aspect, adversarial attacks on deep neural networks, and defenses for them. We'll study how these concepts are related to one another and find out what is the problem that needs addressing. So the metaverse is an integration of the physical and digital worlds that will aim to revolutionize our lives. And the key technologies and the processors that supports the metaverse includes communication technologies like 5G and 6G, mixed reality. However, perhaps the most important of all is digital twinning. Digital twinning is a process that involves the digitization of the physical entity in the metaverse. And among all these technologies that are important to digital twinning is deep neural networks, as they are important in every phase of the digital twinning pipeline, which can be shown here. And here it shows the role of deep neural networks in every phase of the digital twinning pipeline. However, deep neural networks have been found to be vulnerable to adversarial examples. Adversarial attacks can come in the form of digital attacks, physical attacks, and they aim to cause misclassification of deep neural networks or the blinding of deep neural networks. However, there exist defenses to tackle these attacks. But despite there being defenses to tackle these attacks, these defenses, when applied to the metaverse, often tends to be infeasible, as they incur resource constraints and cause trade-offs. The objective of this project is thus to reduce the trade-offs incurred and to improve the feasibility of applying defenses to deep neural networks which support the digital twinning process. As an overview, we provide our method as shown here. We introduce a framework that will balance these factors. They use deep reinforcement learning as an optimizer to alleviate the trade-offs and the resource constraints encountered by defenses for deep neural networks in the metaverse. And by applying this framework at every phase, we can ensure that the digital twinning pipeline can be secured and optimal. In this framework, we also model the communications. Communications is significant in the digital twinning process, hence we saw the need to do so. We also model the data transfer rates and the latency, and the power that is needed for data communications. Trade-offs are inherent when defenses are being applied to secure deep neural networks in the metaverse. And data communication also incurs trade-offs. To balance these trade-offs, we need a solution. And this comes in the form of using deep reinforcement learning as an optimizer to learn optimal strategies. By incorporating realistic scenarios, we can cause a deep reinforcement learning algorithm to be able to learn optimal strategies that will guide our process to ensure that we can alleviate the trade-offs and reduce resource consumption, thus allowing for defenses of deep neural networks in the metaverse to be made feasible. And here's just a summary of our solution, of our framework. To show that this framework is effective, we applied it to a case study which involves optimally securing the digital twin of a smart city, which is supported by 5 autonomous vehicles and 3 base stations. We assume that the deep neural networks are being used here to extract semantic information to create a virtual map of the city as part of the digital twin. This case study, we assume that YOLO v5, an object detector and the base stations are under adversarial attacks. These attacks aim to cause a disruption of the virtual mapping of the city. For this case study, we assume that a physically realizable patch attack is being used. And we use MAP to measure the effectiveness of the attack. So we can see that the attack can cause the MAP to drop by 0.7. And this is our loss function that we use for the attack. For defense, we use YOLO v8 as a patch detector by training it to do so. By identifying the patches, we can nullify attacks. However, we also need to evaluate this defense. And upon doing so, we found that a relationship exists between the MAP and the resolution. As resolution increases, so does the MAP. This also means that we can increase the security of the system by increasing the resolution of the images that is being fed to the detector. However, increasing resolution has a trade-off. It will cause the data size to increase, causing latency to increase and causing the quality of service to decrease. And we know that digital twins require high quality of service. They require low latency. A trade-off thus exists between MAP and network latency due to the resolution size settings. However, we also need to note that base station allocation also has trade-offs. By allocating autonomous vehicles to base stations via distance, we can increase data transfer rates initially. However, allocating too many autonomous vehicles to the same base station can cause intra-base station interference to increase, causing data transfer rates to be lower. Optimal base station allocation schemes are thus needed. For power allocation, while we can increase power to increase data transfer rates, this comes at the cost of causing energy consumption to increase, potentially leaving our autonomous vehicles powerless, draining the battery. And here's just a summary of our framework. We have thus far identified the trade-offs and now we need to optimize them to alleviate them. And this can be done by using PPO, a deep reinforcement learning algorithm, as part of our framework, and by realizing a realistic environment by incorporating the aforementioned trade-offs and the relationships derived between resolution and MAP into the deep reinforcement learning environment. It can allow for optimal strategies to be learned. In particular, from what we just discussed, the trade-offs earlier, we identified that there can be 3 agents in this setting: one for base station allocation, one for power allocation, and one for the resolution settings to control the defense. And we also identified 2 rewards that reward 1 can be given to agent 1 and 2, whereas reward 2 can be given to agent 3. And by assigning penalties when latency falls above a threshold, and also when MAP falls below a certain threshold, we can encourage the agents to take optimal actions that maximizes their rewards. After applying the PPO algorithm, we trained it for 1.6 million steps, and we realized that the rewards converge. Global reward here refers to a summation of reward 1 and reward 2. And upon analyzing the properties, we can realize that no one property is being sacrificed in favor of another: accuracy, latency, and battery consumption all reach optimality. And this proves that our framework did indeed reach an optimal solution, proving that it did work to optimize the defense of the patch detector for the smart city. In conclusion, deep neural networks are fundamental to digital twinning. However, deep neural networks are vulnerable to adversarial attacks and needs defending. However, while there exist defenses to tackle these attacks, these defenses needs optimizing, and this is especially so in the case of the metaverse, as digital twins require real-time support. By applying our framework, we can ensure that defenses for deep neural networks can be made feasible in the metaverse setting. Thank you.